Okay, so we want to find the domain and range of this function y equals square root of 3x plus 12. And well, the square root function isn't defined if the number inside the radical is negative. Okay. So your domain three x plus 12 can't be negative. So what we say is say something isn't negative, you just say it's greater than or equal to 0. And this is easy now to solve. Very simple inequality. So we get subtracting 12 from both sides, we're going to end up with 3x greater than or equal to negative 12. And then Sunday I ran into my allergist. I see him often at the gym. We're talking to him Sunday. He's a generation younger than I am, as are most people, at least. So he was on a machine, usually talk just a couple of minutes, and because we're both there, workout. He said, so I was stretching out, and he walked by and said, "Dave, are the allergies bothering you?" I said, Tuesday was probably my worst day of teaching ever. I couldn't think of the words. I couldn't visualize things and so forth. I said, yeah, it was like that for me in my practice because I've got the allergies too. So I don't know if I can blame it on allergies or just simple inattentiveness, but I wanted to say that 12 over 3 equals -4. And there's supposed to be a negative in that thing, right? I have to slow down my thinking and understand that something's going on and might well have to do with allergies. Okay. Anyhow, -12 over 3, and that equals -4. So the domain is the interval right, infinity signs on the board, -4 infinity. Okay. So does all that make sense? Okay. Good. So there's your domain. Now the range a square root can't be negative. Because if you, we make the convention that the square root is a non-negative number. So the square root of anything is greater than or equal to 0. So if 3x plus 12 take any positive value, it's going to follow that the square root and take any positive value. Okay. Now we can show this. And so we show this a little more rigorously. Intuitively, if this can be anything from 0 to infinity, no, it's 3x plus 12 can be any number from 0 to infinity, then it's going to follow. Now, there's several ways to see that. If x equals -4, 3x plus 12 is 0. So we got 0 covered. The expression 3x plus 12 could be graphed. Okay. And for values greater or equal to -4, well, this thing has a positive slope. And it's equal to 0 when x equals -4. Well, something, a straight line with a positive slope, that's 0 at -4, is going to take any y value at all. It's going to keep climbing. It'll climb through all y values. So that's a bit of insight. It's nice to have. Now we can also show algebraically, but we can show the graph. Zero at x equals -4. Got a positive slope. It takes all positive values. Now, that's pretty persuasive. But we haven't really proved that the square root takes all positive values if what's under it takes all possible values. So what we're going to say is now get really rigorous. We solve this equation for y. Okay. Well, we can square both sides. Y squared would be 3x plus 12, but y has to be greater than or equal to -4. Because we know that if y is less than or equal to -4, we don't have solutions. And we might well have solutions to this equation that are less than or equal to -4. And we don't want to solve this, we want to solve it for x. Anyhow, we want to find an x that gives us the value y. Okay, so solving for x, well, we get we're going to write it out this way, just reverse it. And then we get 3x equals y squared minus 12. And with x will equal y squared minus 12 divided by 3. Now, as it turns out, we don't get any negative solutions. We don't get any negative values of x out of this. Actually, we do. We don't get any values of x less than -4 because y squared is never less than 0. So this is never less than -12. Okay. We can say Ready? Why there is an x that solves this equation. And let's say the equation. Then I can say any x greater than or equal to -4 equal to y squared minus 12 over 3 is a solution of this. Now there's my restriction that x has to be greater than or equal to -4. And I haven't had room to write all that down. If x isn't greater than or equal to -4, then what's under the radical is negative. So we can kind of summarize this. Okay. Solved by this pair of conditions. Gotta have this because it follows directly from what we get when we square both sides. But when we square both sides, there are negative values of y that satisfy this. Okay. Well, yeah, there are values of x that work for negative values of y. And I just talked myself into a circle because you do get x greater than or equal to -4 regardless. So actually, all my discussion of this restriction, you don't really get extraneous solutions here, so that was unnecessary. You kind of want to see that anyway. But we can say this. We can also say this can't be less than -4. Y squared can't be negative. If y squared can't be negative, this numerator can't be less than -12. So the result can't be less than -4. Now that's a whole lot about the domain. Okay, maybe a lot to digest. If you deserve to see that. And the whole question of whether this restriction x greater than or equal to -4 has to be taken into consideration. Turns out that it doesn't. Because this is, but it's still something you want to consider because sometimes you do get extraneous solutions. Now, intuitively, this argument about the graph, okay, probably, well, no, actually in pre-calculus, you're going to want to be able to write this equation down and solve. And hopefully take into account this finer point about restrictions on action. There's another way to do this. Okay. And it goes back to what we were doing last time when we were shifting graphs, transforming graphs by horizontal fifths and vertical fifths and all that stuff. Okay, so we can do this. That we can graph y equals square root of x and transform the graph. How do we graph y equals square root of x? Over math, I can tell you to go ahead and make a table and use your calculator to calculate some of the values. Kind of okay, what's making that number? Okay. Anyhow, I'm going to tell you that's not how we graph the square root. So it's not how I want it graphed in my courses, because I want you to have an immediate understanding of the numbers. And you don't get an immediate understanding of the numbers by doing the arithmetic in your calculator. Also, I want you to see this. I shouldn't have interrupted myself in the middle of my sentence. I want you to see this as I want you to see the graph of the square root function as an inverse of the graph of the squaring function. Now, that's somewhat beyond the scope of this course, but you're beyond the scope of the course, so we're going to do it. Okay. So here's the graph of the square root function. Okay, so there are the values. You agree on those. I know you know how to do that. Okay, so over here, I'm going to make a table. Of x and y equals square root of x. Okay. I'm going to start by doing it wrong. So I'm going to write down some values here. It don't really work, but I'm just going to take the values in this table. And what an inverse function does is it just flips the column. It exchanges the column. So we talked about that? I don't think so. Okay, so in yellow chalk, I'm going to write down some of the values in the column in yellow. Then I'll write the rest of them in white. I'll explain in a minute why I do that. Okay, so I just take the right column of this table and make it the left column. Then I take the left column and make it the right column. Well, the left column is -2, -1, -1/2. Zero, 1/2, 1/4. Okay. Now, this part is my inverse function. In this part of the table, we're going to discard. I probably want to know why we discard this part of the table. I'll explain it a little more when we get a picture of here, but it's because if we include this part, we don't have a function. Now, I don't know how much we've talked about the definition of a function. Definition of a function is you just have one y value for a given x value. If I tell you what x is, you tell me without any ambiguity what y has to do. Well, you notice that if x is 4, I got 4. Now, if I'm going to include this, if x is 4, you get -2. You can't get two y values the same x value. Now, over here, it was fine to get two x values for the same y value. If we didn't do that, we wouldn't have a nice parabola. Okay, and that's not any reason for saying that this is okay. It's simply that the definition of a function, the condition for a function is that you only get one y value for any given x value. There's no x value, gives you two y values. So something's got to go. We got to discard some of these values here if we want this to be a function. And the convention is for the square root function, well, the square root can't be negative. Okay. Well, that makes perfect sense too. We discard this because we know that the square root of 4 is not -2. Because we define the square root to be a positive number that you square to get the result. Okay. Now there are two numbers you can square to get 4. Yeah, -2 and 2, and I wrote down 4 here. I could have written down 2. Again, there are two numbers that we can square to get 4. -2 gives us 4, 2 gives us 4, right? But there aren't two different square roots of 4. Only the 2 is the square root. Okay. Hopefully we have an idea, so we're going a little further. Well, now if we look at these graphs, again, I'm not going to label these points because I think we understand. This is -2. This is 2. This is halfway between 0 and 2, so it's 1. This is halfway between 0 and 1, so it's half. And up here, it'll be 4, and then halfway from 0 to 4 should be 2. And then we're going to get 1 halfway between 2 and 0. 1/2 halfway between 1 and 0, and 1/4 halfway between 1/2 and 0. And we can easily sketch the points. According to our table. Actually, one of my better offers, I would say any huge obvious flaws. Doesn't always work out that way, okay? Now what I'm going to do is Then I use yellow chalk to indicate these 3 points of the x squared graph that don't correspond to points of the square root graph. And I'm going to make this half of the curve yellow. So now I'm going to draw the graph of the square root function. Very easy. I've got to have 4 out here now. There's 2. There's 1. There's 1/2, and there's 1/4. So I label my x-axis just like I labeled my y-axis up here. Reason for that should be pretty straight, pretty easy to understand. I've switched my x and y columns, so my x's have become y's, and my y's have become x's. The x's in this graph have become y values for this graph, and the y values for this graph have become x values. The y values become the x values, then my interval from 0 to 4 has to be down here on the x-axis. And similarly, my interval from 0 to 2 is going to be on the y-axis. All right, which will be a little bit hard. Do the way it is. Okay, now and locate these points. I got 0, 0. I've got 1/4, 1/2. I've got 1, 2. And all the way up here, I've got 2, 4. So there's a picture of my square root graph. And it always has this shape. Sometimes it's distorted, sometimes it's stretched, sometimes it's compressed. I can also little something extra. Here's 4. Here's 3. I can sketch this part of my x squared graph on this scale. We're going to go through the point 1, 1. Got the point 1/2, 1/4. I got the point 0, 0 and the point 2, 4. So here's my graph of this part of the squaring function. Here's my graph of the square root function. I'll label this graph y equals x squared, x greater or equal to 0. Why is x greater or equal to 0? Well, again, we can only use x values greater or equal to 0 from this graph because the y values of this graph can't be less than 0 because square root, again, has been defined to be a number greater than or equal to 0, whose square equals number. Okay. Okay. So down here. Here's y equals square root of x. Okay, well, what does this have to do with the domain of this function? So what does this function have to do with this function? Turns out it's a vertical stretch and a horizontal shift. So let's see how that works. Are you glad you asked this question? This is something that it's a lot to digest, but I want you to see it. And then if you're inclined, you go back and look at the video. Keep it in mind because it'll eliminate a lot of stuff. In the first part of the pre-calculus course, you'll be one of a few students that understand. Okay. Okay, so we've got y equals the square root of 3x plus 12. That's 3 times the square root of x plus 4. Well, that's a square root of 3 times the square root of x plus 4. Now, square root of 3 is about 1.732. I'm just going to use 1.7 because you're not going to be able to visualize 1.7. You're not going to be able to distinguish visually 1.732 from 1.7. Now, we're not going to be able to graph this thing accurately enough to make that difference. Okay. So for our purposes right now, 1.7 is a sufficiently accurate approximation of the square root of 3, although if you want to calculate this, well, it's better calculate this with a calculator or a computer. You're not going to bother vertically stretching this thing and then horizontally shifting it. You're just going to plug those numbers in. Okay. And it's going to work. But if you want to understand the graph, then you want to do this stuff. Okay. Well, what does a vertical stretch do? If you vertically stretch this square root function by a factor of 1.7, you move every point 1.7 times further from the x-axis. We talked about that last time. Then we look at what y equals square root of x plus 4, right? It's a horizontal shift of -4 units. Now, I should have reviewed what we did last time. We talked about horizontal shifts. I think we did. I think we covered vertical stretches and shifts and horizontal. Just want to make sure we did. Okay. Okay, so that's pretty cool. We have all the ideas that we need now. To sketch a graph of y equals square root of x plus 4. So. That's what we're doing. Well, I thought I was thinking this through before I drew my graph, but I didn't think it through well enough. I knew I needed more room to the left. Didn't give myself nearly enough. So let's put the graph here. So I'm going to put -2 here. 2 here. And 4 down here. 2. And okay. Now I'm set up. I can plot my points again. Now I don't have the table visible right now, so let's move it over. I can look at my table again. Remember how this table came from this table by reversing. And incidentally, we call these inverse functions. Well, I did use that terminology. Okay. It's what we always do and create an inverse function for one of our toolkit functions. You have to think about what word to use. I'm trying to use toolkit. Toolkit, parent, basic, those terminologies are equivalent. So, anyhow, here we are. Here we are. Here we are, and here we go. First thing we're going to do is we're going to do the vertical stretch. We want to do that first because it involves multiplication. The vertical stretch because square root of 3 is a multiplier. And by order of operations, multiplication happens first. So we want to do any multiplications first. We want to do the transformations that involve multiplications first. Meaning we're going to leave our horizontal and vertical shift until last. They can be done in any order. But let's do a multiplication. Okay. Well, we multiply all our y values by 1.7. That means what to use it. Oh, the purple chalk I can lay my hand on easily. I actually got a whole box of chalk. Right. Anyhow, okay. So if we draw a vertical arrow here and a vertical arrow 1.7 times this long, and 1.7 is between 0.7 is between 0 and 1. And it's about 2/3 of the way to 1, so I say a little more than 2/3. So we draw an arrow about 2/3 as long as this one. And we get our new point. Of course, we do that calculation in our head. This point should be at about 1.7, maybe have it a little high, but it's okay. Okay, then this point is 1 unit from the x-axis. We want to go 0.7 units above that. And then when X is 4. That's our Y value. And we do 7/10 of that. We go to be about this long. So we come up to about there. And we can do the arithmetic. You know, this is 1/2. 0.7 times 1/2. Well, 1.7 times 1/2 is 0.3. .85. Okay, I'm not thinking about this thing, and nothing was clicking, sorry. So that would be about 0.85. This would be 1.7 times 1, just 1.7. That looks about right. And this should be at 1.7 times 2, because this is 2, 1.7 times 2 is 3.4. So if I put 3 here, which is about where it would go, it's reasonable that would be 3.4. And of course, 0 doesn't go anywhere, y equals 0, y equals 0. So okay, so what we have is y equals the square root of x. What we have up here is y equals square root of 3 square root of x. What we want to get is y equals the square root of 3 times the square root of x plus 4. If we replace this x by x plus 4, that's going to shift the graph 4 units to the left. Because in order to get the same y value, x is going to have to be 4 units greater. Which means, well, we talked about it last time. I want to complete that sentence, but not messing up. So what we're going to do is we're going to shift every point 4 units to the left. Okay, so this point, which is at x equals 4, ends up here. This point, which is at x equals 1, ends up over here. Okay, well, that's roughly the same. That's kind of okay. And then this one's going to move over 4 units, and this point's going to move over 4 units, and this point's going to move over 4 units. Didn't do that real well, but you get the idea. The reason I know I didn't do it real well is this should be about x equals -4. -2 is here, -4 is a little further along. So I didn't quite go far enough. But now if I sketch my curve, it's identical in shape to the vertically stretched curve, y equals square root of 3. Okay, but it's moved over 4 units, and this is y equals the square root of 3 times the square root of x plus 4. And that is equal to the square root of 3x plus 12. Now, why are we doing this? Well, first of all, it's really neat. Second, if we understand these transformations, we get a visual picture of why the domain is what it is, even though we can understand that quite well using other methods. But really what we're after is the domain. So what's the domain of this function? Well, as I've graphed it, the domain starts here at x equals -4. And of course, back several years ago, we included algebraically and graphically, talking about a straight line graph that didn't talk, that the domain is -4 to infinity, right? Well, is that consistent with what we have here? Yeah, we haven't graphed the entire function. So I can kind of put an arrow on this. And I can put an arrow on this. And if I can find that good for the talk, I can put an arrow on this, indicating that it goes on. We also know that the thing never levels off. As x keeps getting bigger, so does the square root. And we can, might as well say all of it. Okay. I'll come back to what I was just saying. But here we have. Minus square root plus 3 graph is -4 infinity. Ultimately, because the domain of the square root of x is square bracket in closed interval, half closed interval, 0 to infinity. Why? It's no matter how big y is, it means this equation means y squared equals x. There is an x. Such that y equals square root of x. No matter how big you want y to be, just square it. And that tells you that that's the x. Okay. It gives you the value y. Very simple idea, but one that's a little hard to grasp at first. Okay, well, there's a whole lot of content there. And what we've got. Okay. Yeah, I would go back and look at this graph. And as much of that as you understand, you totally understand it now, whether you choose to review the video and really nail it. I think you're gonna be in good shape to understand the stuff that you see in the early part of the pre-calculus course. First chapter of pre-calculus is one where we do all this stuff.